Good afternoon and welcome you all for today's discussion. So yesterday we have discussed about flow between two fixed parallel plates. Today we are going to discuss about flow through pipe. Flow through pipe, because this is one of the most important engineering application, as we know that crude oil and water and so many fluids are transported from one place to other place. We know that for long distance, when there you can say refineries, crude oil is transferred from one place to another place. So here we are going to discuss Hagen Poiseuille Law, and this is a flow through pipe, and there are so many engineering applications, transportation of the oil, crude oil from very long distances. You see that India is planning to get crude oil from Saudi Arabia, underwater crude oil transporting lines, and you can see here in India so many refineries are there, and we get crude oil transported through pipe, and water distribution lines here also follow this same principle. So it's very very important. ये बहुत ही important है कि हमें मालूम होना चाहिए कि what is a pressure drop. जब oil या water या कोई दूसरा fluid या gas या because natural gas is also transported through pipes, so we must know what is a pressure drop. What is, because due to frictional resistance that will occur due to flow of the because will have a certain viscosity. Due to this viscosity, when oil will flow through the pipe or water will flow through pipe, wall resistance due to internal resistance of two layers, adjacent layer resistance will develop, shear resistance will develop, and wall when it will move through the wall, it will come in contact with the wall. So frictional resistance, due to this frictional resistance, pressure drop. Pressure drop will take place, and we have to calculate what is the pressure drop, so that we can calculate what is power required to transport oil from one place to another place, or any liquid from one place to another place. That's why this is one of the most important topic of the fluid mechanics, and you will always see at least one question in engineering examination, any examination where you will take mechanical engineering as a optional subject, whether it is a IAS or engineering service or GATE examination or any publicity. You will always expect one or two questions from this topic. So now let us see what is how we calculate. So now make a segment of pipe. First we make a segment of pipe. So this is a cross section, some segment of pipe we are taking here. This is the cross section of pipe, and you see this is a pipe cross section, and this is one is a center line. This is a center line of pipe. No, this is a, and we will take a reference line here. Let us take, this is a reference line. This one is a reference line, and this is direction X, and this is direction, you will see direction Y direction. And here fluid is flowing along this direction. This is a fluid is flowing along this direction, and diameter of the pipe or is a radius. You see this is diameter of the pipe, this is a diameter of the pipe. So you take a radius, one will be radius R, capital R is the radius of the pipe. So for analyzing flow, we will take very small element. This is a small element. We take a small element of radius R. This is a small element of radius R, and this is radius R. Small r. Small is a radius. Small r is radius of this small element. Length dx. Suppose this small element is moving along this direction. It is moving along this direction. So it will experience shear resistance. Shear stress will occur over the surface. So shear stress will be like this, and shear stress will be like this. In opposite direction, shear stress will act, that is tau. And this element from this reference line is distant at distance y, and flow is fully developed. We are considering in the region, we have taken in this region that flow is fully developed, and suppose this is a velocity distribution, you can say here we can make a velocity distribution here like this. This is like a velocity distribution, and at this point, this is the distance y, at distance y, and velocity at this point is u. Velocity at this point is u randomly, because the velocity throughout the pipe is varying. Velocity will, if it is a laminar flow, and here you will find u maximum velocity at any point from the reference line distance y, and if it is also at distance y, velocity is u. U is a random velocity at any point. So this is a defining, because you know that here pressure is p at due to surrounding pressure. Here is p, and when we move df distance, then pressure will become, because pressure is a function of distance. As we move along direction of flow, pressure will decrease or increase. So there is a variation in pressure p plus del p over del x dx. This is pressure at another end. This is pressure p at this place, and when we move direction dx, then pressure become p plus del p by del p over dx. Total pressure. So under this flow is steady state condition. Under steady state condition, net force acting on this element will be zero. Otherwise, if there is unbalanced force, then it will accelerate. So it will, acceleration means unsteady flow. So flow is not accelerating, but it is steady. So this element is not experiencing any external force. So what is the net force acting on this element? What is net force acting on this element? That we want to calculate here. So make it small. So what is net force acting on element that we have selected of the length dx and radius r? So net force acting sigma fx should be equal to 0, because we know that no force is acting on this element. So net force equal to p minus p plus del p over del x dx multiplied by area. So it becomes force. Area is a pi r square, and minus shear stress, because shear stress, this element will experience resistance from the shear stress. Due to this shear stress, force is acting opposite to direction of movement of this element. So that will be equal to tau. Tau is shear stress into area 2 pi r dx. If it is tau into 2 pi r dx, this is area, that will be equal to 0. So now solving this equation, we get this will be eliminated. Minus del p over del x dx into pi r square equal to 2 pi r dx into tau. So dx will be eliminated, pi will again be eliminated, 1 r will be eliminated. So my del p over del x equal to 2 upon minus 2 upon r tau. So what is tau? Here because we have taken reference line here from 0 0 along at y distance, so we can define tau from Newton's second law. Newton's law of viscosity, tau equal to mu du over dy. U is local velocity at this point, and dy is distance. So here how we can change, because we know that y equal to r minus small r. Y equal to capital R minus small r. So dy equal to 0 minus dr, because r is a constant, so differential of r will become 0. So you can replace dy by minus dr. So tau equal to minus mu du by dr. Putting value of tau here, and you know that del p is a pressure gradient is a function of x only. So you can write partial differential into exact differential. You can write dp over dx equal to minus plus 2 mu upon r du by dr. So we can further write du over dr equal to r upon 2 mu dp by dx. This is the equation that I want to derive first. This is the first equation that I want to derive. Now this is the equation of velocity. How we can find from this equation velocity u at this point? Now eliminating this one. Let us eliminate this one. So this one is du over dr equal to r upon 2 mu dp over dx. Now integrating this equation with respect to r, integrating whole equation with respect to r, so you get u equal to r square upon 4 mu dp by dx plus constant c. This is equation number 2. Now applying boundary condition, because this constant we have to find out. Now applying boundary condition. What is boundary condition for getting c at r equal to capital R? We know, because this is a wall, r equal to capital R, condition of no separation will apply here. So u become 0, u become 0 at r equal to capital R, condition of no separation. This is under condition of no separation. When fluid will come in contact of the wall, velocity becomes 0. Whatsoever velocity may be, maximum velocity, but at the wall surface, velocity will be equal to 0. So 0 equal to capital R square upon 4 mu dp by dx with plus c. So c equal to minus R square upon 4 mu dp over dx. And putting this value in equation, we get general equation of u equal to r square u equal to r square upon 4 mu dp by dx and minus r square upon 4 mu dp by dx. Taking some common, so u equal to 1 upon 4 mu common minus dp by dx and in r square minus small r. This is a general equation of velocity at any point in the pipe. किसी भी point, at any point पर you get, by using this equation you get velocity at this point. Now the get what is a condition of maximum, because you know that this is a parabolic. This equation you get at coordinate. So this is a equation of parabola. So for maximum velocity, what is condition? Because this is varying, where velocity will become maximum. So du over dr should be equal to 0 for maximum velocity. Differentiating this equation, 1 upon 4 mu minus dp by dx, 0 minus 2r. So when we equate this one equal to 0, you get r equal to 0. For r equal to 0 means the central line. Here we have measured r from here. When r becomes 0, you see velocity become maximum. When r becomes 0, small r becomes 0, velocity become maximum. So what is the maximum velocity? U maximum equal to 1 upon 4 mu minus dp over dx into r square. This is the maximum velocity and this is the maximum velocity. So this is the maximum velocity you get, and the two things that you have to remember: general equation and maximum velocity. General equation and maximum velocity. So this one is general equation, u equal to 1 upon 4 mu, minus dp over dx, r square minus small r square, and u maximum equal to r square upon 4 mu minus dp over dx. This is equation number equation number 3 and equation number 4. So u maximum you get, this is u maximum velocity. And let us find what is a shear stress distribution. Already we have defined what is shear stress. So tau equal to mu du over dr, that we have defined. Tau equal to minus mu du over dr. So again differentiate u with respect to r, we get minus mu d upon dr, and that is 1 upon 4 mu minus dp over dx, r square minus r square. Differentiating this equation with respect to r. So common constant you take out from the bracket, so it become minus 1 upon 4 minus dp over dx in bracket 0 minus 2r. So it become r upon 2 minus dp over dx. So this is general equation for shear stress. where shear stress will be maximum. Putting what are condition of max, because this is a linear equation, shear stress distribution is linear, no quadratic equation. So shear stress distribution is linear. So where shear stress is maximum? From C, because R is only variable thing. So for this element R is a variable. So where shear stress is maximum? For R equal to capital R, tau equal to tau maximum, and for R equal to 0, tau equal to 0. At center line shear stress will be 0, and at the surface of both surface of the pipe shear stress will be maximum. So distribution of shear stress will be like this. So maximum shear stress tau maximum equal to R by 2 minus dp by dx is always positive quantity. Always positive quantity. This is always positive quantity. Tau equal to R by 2 minus dp by dx. If it is always a positive quantity, minus dp by dx is always positive quantity, because pressure gradient along this direction is always negative. When we go from higher pressure to lower pressure, P2 minus P1 is always negative. So this quantity already one negative is there, and dp by dx is already negative, so negative becomes positive. So this value is positive. So tau maximum distribution of shear stress will be like this. Distribution, we can make distribution here, make separate diagram of purpose like this one. If we say distribution of this pipe, and distribution of shear stress will be like this, This is a shear stress distribution. At R equal to 0, shear stress is 0, tau max here, tau max here, and these are varying. At this point tau equal to 0. At R equal to 0, shear stress becomes 0. Same pipe we are considering here. So now let us find what is the average velocity, because all engineering practical purpose, for finding out pressure difference, pressure gradient, loss of pressure in terms of the head. So we always use average velocity because all calculation, pressure drop, power required are based on the average velocity. That average velocity you can define like this. What is average velocity? This is a average velocity, V average. So we have to find out V average. Average velocity means average of whole varying velocity. How we can calculate average velocity? So let us make another diagram for finding out average velocity. So in same pipe, we take same pipe, and here let us see. This is a circular cross section, because we know that cross section of the pipe is circular, make a projection of circular cross section. This is a circular cross section. At radius R, take a small strip. This is a small strip of radius R and dr. This is a small strip of thickness dr. And at this point, velocity is u. So what is a discharge taking place from this radius? What is discharge taking from this radius? This small strip, how much discharge is occurring from this stipple area? It is R distance from the center, and thickness is dr. So a small quantity of the fluid that will pass through this strip we have to calculate. So that will become dr equal to dq. So dq equal to 2 pi r dr. This is area of this strip. 2 pi r dr is area of this, and multiplied by velocity u. You can find out discharge. So total discharge equal to Q equal to integration of 2 pi r dr into u from 0 to r. If we integrate this strip for 0 to r, we get full discharge from this pipe. 0 to r, a small quantity fluid flowing through this dr thickness strip, and integrating this small quantity dq for whole of the area, whole of this cross section, we get total discharge. That is equal to, putting value, taking 2 pi outside, it is a constant, 0 to r, and putting value of u, 1 upon 4 mu minus dp by dx into r square minus r square. Again taking out constants. So 2 pi upon 4 mu and minus dp by dx. In bracket only we get 0 to r. You get r square into small r minus r cube and dr. And integrate this one. We find out total discharge. We can find out total discharge. That will be equal to q equal to 2 pi upon 4 mu minus dp by dx into r to power 4 by 2 minus r to power 4 by 2 minus r to power 4 by 4. Solving this one we get total discharge but u divided by 2. So it will become q equal to pi upon 8 mu minus dp by dx, and you also here r is r to power 4. That is a total discharge from this pipe. We have to find out average velocity. So we have to find out V average equal to q upon cross sectional area pi r square. This is the cross sectional area. So dividing this equation by pi r square, pi r to power 4 upon 8 mu to pi r square minus dp over dx. So pi r square will be eliminated. So V average is equal to r square upon 8 mu minus dp over dx. This is equation for the average velocity, and for all practical calculations we use this average velocity, whether we have to find out Reynolds number, whether we have to find out pressure lost, whether we have to count out pressure gradient, whether we have to find out the power required to maintain the flow. All practical purpose required average velocity. This is the most important step of this calculation. So now average velocity we have calculated. So let us remove this one, and from this average velocity we can find out what is ratio of maximum velocity u maximum upon v average velocity. That is equal to, here you see r square upon 4 mu minus dp over dx, and average velocity r square upon 8 mu minus dp over dx. So it will be eliminated. You get equal to 1 by 2. This is very important. Maximum velocity upon v average velocity ratio is 1 by 2. From completion point of view, objective type questions, you have to remember. If you have derived this equation, you certainly remember what is for laminar flow. For laminar flow, what is a ratio of average velocity maximum? Sorry, we have I think written that should be equal to 2, not 1 by 2. That is equal to 2. There is mistake in writing because this calculation is reversed. So u maximum upon v average equal to 2, or v average upon u maximum equal to 1 by 2. This is, you can say, either maximum velocity upon average velocity or equal to 2, or average velocity to maximum velocity equal to. This is more comfortable because this is higher, this is lower. So average velocity is always less than maximum velocity, and ratio of average velocity to maximum velocity for laminar flow through pipe is always equal to 1 by 2. This is one of the most important observation of this calculation. So again, now we have to find out pressure gradient. What is pressure gradient? Means what is pressure lost? So by using average velocity. So already we have average velocity. So by using average velocity, we can find out the pressure gradient. This is average velocity. V average equal to r square upon 8 mu minus dp over dx. dp by dx minus equal to 8 mu v average upon r square. Taking dx and right side, minus dp equal to 8 mu v average into dx upon r square. So integrating this equation again, minus dp 1 to 2 equal to 8 mu v average upon r square dx. 1 to 2. We get here P1 minus P2 equal to 8 mu V average x2 minus x1 upon R square. So P1 minus P2 is delta P and x2 minus x1 is a length up. Suppose we are considering from x1 here and x2 here. This is length 2 points we are measuring. So this is you can equal to L. You can denote this difference of 2 coordinates along f axis equal to L. So you can write P1 minus P2 equal to 8 mu V average velocity into L upon R square. We can get pressure gradient, pressure loss per unit length, pressure gradient P1 minus P2 equal to 8 mu V average upon R square. Sometimes we have to define this loss of pressure in terms of the head loss. Means in what is the height, what is the length of the head loss? Means head loss in terms of the water column. So we divide the specific gravity of the water, then we get a head loss in terms of the water column. So P1 minus P2 upon specific gravity of the water omega equal to 8 mu V average into L upon omega R square. So this is the equation, and again we can write the equation in terms of the discharge. Sometimes we can define it in terms of the discharge rate. So this is equal to HL. This is equal to head loss, total head loss. On that basis, we can find out power required. How much power required to maintain the flow? Because once you get head loss, then you can get power required. So power required equal to, we know, omega Q into head loss HL upon 1000. If you divide it by 1000, then you get unit kilowatt. So power required, you can give omega is specific weight of water or specific weight of the liquid, any liquid. Q is discharge rate, HL is head loss, and 1000 by dividing 1000 you get power in terms of the kilowatt. So this is complete discussion, and we will also solve questions so that you can solve question based on the Hagen-Poiseuille law. This is also known as a Hagen-Poiseuille law. Most important derivations comprising of all terms, very useful for solving, because this is a case where most of the practical applications you will find, whether it is supply of water from the reservoir to turbines, supply of water distribution lines in domestic and cities, urban and rural, supply of the water, urban and supply of the oil, supply of the gas. Everywhere you will see that this is a pipe. So we have to calculate power required and head loss. Once we know head loss HL, then we can find out what is the power required to maintain the flow throughout the length of the pipe. This equation you can also express in terms of the discharge. So P1 minus P2 upon omega equal to 8 mu V average L upon omega R square. Discharge, you know that V average equal to Q upon pi R square. Putting value of Q upon pi R square, that will be equal to 8 mu Q L upon omega R to power 4 and pi omega R to power 4. So you see that head loss HL is proportional to discharge Q length L and inversely proportional to radius, or we say inversely proportional to diameter also, because radius will become d by 4. Again power remains same. So HL total head loss is proportional to viscosity, proportional to rate of discharge, proportional to length of pipe, and inversely proportional to radius of the pipe or diameter of the pipe, and inversely proportional to specific weight of the fluid. So this is a very, very important point from the completion point of view, whether it is engineering examination, IES examination, or GATE examination, any public sector examination, these terms are very useful for you to understand the concept. Thank you very much for watching this video, and please like and subscribe and share it to your friends. Have a nice day.